Okay, so our next speaker will be Kifung Chan, who will speak about mirror symmetry of non-abelian actions.
Yeah, thank you for the introduction and thank you for the invitation. So this is a joint work with Conan Leung. We study the mirror symmetry for action of non-abelian groups. Okay. Uh, sorry. Okay, so let me begin with the setting. Oh, sorry. Uh, Let me begin with the setting. So we let X be a symplectic manifold and let G be a compact Lie group and such that G acts on X in a Hamiltonian way. So it has a moment map. And let T be a maximal torus of G. So you can restrict the G action to T, and so that the T action on X is also Hamiltonian. So you restrict the action to T, and also you restrict the moment map to T. Okay, and let LE be a sorry. Do you hear echoes? Okay, then not better. Okay, so let L be a Lagrangian brane, LE be a Lagrangian brane, which means that L is a Lagrangian of X, and also E is a unitary flat line bundle on L, and such that the T is acting on L, which means that L is invariant under the T action. So G is acting on X, but L is invariant only under T. Okay, so in particular, it implies that the moment map, the T moment map is constant on L. So the the mu TL here is in fact a number in the Lie algebra dual. So let me go to the theorem. The theorem says that, so suppose we have a Lagrangian brane, so suppose the floor cohomology of this Lagrangian brane is not equal to 0. Then there are two consequences. One is the moment map value would be contained in the center of the Lagrangian group. And the second is the holonomy of E is also in the center of the Lagrangian group. Yeah, I will explain the terminology. So the G chat here and the G chat here are both refers to the Lagrangian group. So in this talk, the only Lagrangian group will be SUN and PSUN. Okay, so when G is equal to SUN, then G chat is equal to PSUN, and vice versa. So in particular, if you take n equals to 2, then SU2 and SO3 are Lagrange dual because PSU2 is equal to SO3. And there is also a compacified version. So you compacify everything. So SUN, you compacify, it becomes SLNC. And you compacify PSUN, it becomes PSLNC. Okay, so these are the only Lagrange dual groups that we will be using in this talk. Okay, and an important fact about the Lagrange dual group is that if T is a maximal torus of G, okay, then we can consider the dual torus, which is the set of homomorphism from pi1 of T to U1. Okay, then T check will be a maximal torus of G check. Okay, so in the theorem, the holonomy here is in fact an element in T check. Okay, and T check is a subset of G check. So it makes sense to say whether the holonomy is an element of the center of G check. Okay. And similarly, it also makes sense to say that the moment map value is in the center of the Lie algebra G check. And moreover, for the Lie algebra part, there is a simple description. So the moment map value is contained in the center of G chat is equivalent to saying that that moment map value is fixed by the while group. Okay, so for the Lie algebra part, that theorem say that the moment map value is fixed by the while group. Okay. Any questions? Or I will give you an example. Okay, so suppose X is equal to P2 and G is equal to SU3. So which means the maximal torus is T2, the two-dimensional torus. And that triangle is the moment map image of P2, the moment polytope. Okay, so the triangle is contained in the Lie algebra dual. Okay. And now we see that the only T2 invariant Lagrangian in P2 is the fiber over that point. Okay, is the central fiber. Okay, which is exactly the point in the Lie algebra that is fixed by the while group. Okay, in this case, the while group action on how to has only one fixed point, which is a 0. Okay, a similar example. So if you blow up a point in P2, so it is a blow up of P2 at a point, you still have the T2 action, but you do not have the SU3 action now. So, but this time you only have SU2 action. Okay. So this is the moment polytope for the T2 action. So you can project everything to the Lie algebra dual of S1, the maximal torus of SU2. Okay. So in this case, there are two torus fibers that have non-vanishing flow cohomology, and both of them are lying in the pre-image of 0 here. Okay, and that 0 is the only fixed point of the while group action. Okay, so this example is for the moment map part. You can also check that this example also satisfies the holonomy part. Okay, but I will give an easier example to see the holonomy things. Okay, so suppose X is the S2 or equal to P1, and let the S1 be acting on the S2 by just the rotation. So this time, the only S1 invariant Lagrangian with non-vanishing flow cohomology is the Greek circle. Okay, once again, this is the only S1 invariant Lagrangian with 0 moment map value. Okay, and also we see that the holonomy can only be 1 or -1. Okay, and this fits with our theorem because the S1 action in fact extend to an SO3 action. And the G check for SO3 is equal to SU2. And the center of SU2 is plus or minus 1. So our theorem says that if the flow cohomology does not vanish, then the holonomy can only be plus or minus 1. So this fit into this match with our theorem. So there's a similar example. So still S1 acting on the sphere, but the action is the square of the piece of the previous one. So the speed is doubled. Okay, so this time this S1 action can extend to an SU2 action. Okay, because the speed is doubled. So we go to the double cover. And now the G chat is equal to SO3 and center of G chat is equal to 1. Okay, so in our theorem, we say that the holonomy along the T orbit has to be in the center of the dual group. So in this case, and S1 orbit is 2 times the equator, right? 2 times the great circle. Okay, so the holonomy along the equator is equal to plus or minus 1. So holonomy along an S1 orbit can only be 1. So that also matches with our theorem. So any questions so far? Okay. So okay. So in the remaining time, I would like to explain the relation of our theorem with 2D mirror symmetry as well as 3D mirror symmetry. Okay. So the title of my talk is Mirror Symmetry for Non-Abelian Actions. So it may be better to record something about the mirrors for T action, for our abelian actions. So many of this thing is due to Telemann. Okay, this is some physical statement. So you have a Hamiltonian T action on a symplectic manifold. This will give you a boundary condition in some 3D theory, or a boundary condition in the Higgs branch of that 3D theory. And the 3D mirror symmetry says that it should also give you a boundary condition in the Coulomb branch. So basically, understand the Higgs branch and the Coulomb branch are 3D mirror to each other. Okay, so there's some physical reasoning. So mathematically, what does it mean? It means that if you give me a Hamiltonian torus section on X, then the Coulomb branch, you should produce a complex Lagrangian in the Coulomb branch. Okay. So in the abelian case, the Coulomb branch is very easy to describe. So in the abelian case, the Coulomb branch for T is cotangent bundle or TC check, the cotangent bundle of the dual complexified torus. So it is a complex symplectic manifold. So we can talk about its complex Lagrangians. So the 3D mirror symmetry asserts that if you give me a Hamiltonian T action on X, then there should be a complex Lagrangian in the Coulomb branch, which is equal to T star TC check. Yeah. Okay. So the interesting thing is that there is a way to construct that complex Lagrangian using SYZ mirror symmetry. Okay, using SYZ that I'm going to discuss. So let me assume we are in a very good situation. So that, let's say, suppose X is scalar, and let's also suppose we have an anti-canonical divisor of X, and everything is T invariant. Okay. So we can define X check, which is the set of Lagrangian brane, LE, such that L is a T invariant special Lagrangian in the complement of D, and E is a flat unitary line bundle over L. Okay, so it is proved by Owu like 20 years ago that X check also has a Taylor structure, and it also equipped with a holomorphic function called a superpotential. So the F is defined by an infinite sum, so there is some issue about the convergency, but let me just assume it converges for simplicity. Okay. On the other hand, so because now we are using T action, you can also define a map using the T action. You can define a map from X check to TC check. Okay. So TC check is equal to T check times T star. Okay. And then that map pi check is sending a point LE to 2 components. So for the compact part, it is equal to the holonomial E. for the non-compact part is given by the moment map value of L. So we can check that this is holomorphic. So this map is just one map. You do not need to take infinite sum. So no convergence issue. Thank you. Okay. Okay, so now we are in this situation. So we have X chat and we have a function f, and also with a map to TC chat. So there's a way to produce a Lagrangian in T star TC chat that called the generating function. That's a method in classical symplectic geometry. So let me give you an example. Still the same example. So S1 acting on P1 with the standard action. So the 2D mirror X chat is equal to C star. Okay. And the superpotential is X plus 1 over X. And the map to the TC check, which is C star, is the identity map. But I use Z to be the coordinate of TC check and X to be the coordinate for X check. Okay. And then this is the Lagrangian. Okay. So to obtain the Lagrangian, you basically take the differential. So df is equal to z minus 1 over z times dz over z. So the graph is given by the equation x equal to z minus 1 over z. Okay. And now the second example, S1 acting on P1 but with speed doubled. Okay. So x chat and f are still the same, but the map to C star is the square of the previous one. Okay. And now this is a Lagrangian. So once again, you calculate df is equal to distance. So the equation for the Lagrangian is x equal to this guy. Yeah. Okay. So in this example, you see that for example 1, the intersection of the Lagrangian with the zero section is plus or minus 1 equal to the center of the dual group. And for the second example, the intersection of the Lagrangian with the zero section is equal to 1, also the center of the dual group. Okay, so that's the geometric picture for our theorem. So our theorem actually says that if the T action on X, so Ts on X will give you a Lagrangian in T star TC check. And if the action extend to a non-abelian G action, then the Lagrangian Lx has to satisfy the following property, says that the intersection with the zero section has to be contained in the center of the dual group. Okay. And of course, this is related to 3D mirror symmetry. So previously, when you have a T action, you expect to obtain a compact Lagrangian in the T Coulomb branch. Now you have a G action, non-abelian G action, then you expect you also obtain a compact Lagrangian in the G Coulomb branch, the 3D theory Coulomb branch. But the problem is for non-abelian G, the Coulomb branch is not that easy to describe. Okay, so there is a relation between the G Coulomb branch and the T Coulomb branch here. So W is a while group. So while group is acting on T star TC check. So you can take the quotient. And then the guy here is the middle guy is the blow up of this guy as some subset set. Okay, as some complicated subset set. And the Coulomb branch G is an open subset of the blow up. Okay. If the G is rank 1, then both sets can be described easily. So for the second step, the blow up locus is just the center of GC check at 0. And the Coulomb branch is an open subset of the blow up by removing the proper transform of the zero sections. So yeah, that's in rank 1, it's easier to describe the Coulomb branch. So So you using the description of the non-abelian Coulomb branch in rank 1. Okay, so it is easy to show the following. So compass Lagrangian in the non-abelian Coulomb branch is in one bijection with W invariant compass Lagrangian of the T Coulomb branch such that its intersection with zero section is transversally, and the intersection are only at the center of G or G check. Okay, and our theorem says that the T Lagrangian will satisfy the second condition, so it will give you a Lagrangian in the non-abelian Coulomb branch. Okay. So finally, just a final remark. So all the examples I give you are about rank 1 group. For high rank, the theorem A is not enough, so we need to prove something stronger. And this is theorem B. Okay, so we call F is the superpotential and DF is the is a differential of the superpotential. So I regard it as an element in the first homology of L, maybe with some non-weak coefficients. Okay, and this is theorem B. So let alpha be a root of GC check. Okay, so G check is a compact group, so it has a root system. So alpha be one of the root, and S alpha be the corresponding simple reflection. Okay, and there is a homomorphism from the first homology from the homology of T to homology of L. This is because T is acting on L, so the orbit map will induce a homomorphism in the homology. So the theorem says that suppose DF is contained in the image of this guy. This is a subspace of the first homology of T fixed by the simple reflection S alpha. So suppose DF is in that image, then pi check. Okay, so remember pi check is the map from X check to TC. So that pi check is equal is the map from X check to TC check. Okay, so given by sending LE to mononomy of E and moment map of L. Okay, so this is pi check. Our theorem says that if DF is contained in that image, then pi check will be contained in the kernel. So in fact, that theorem B will recover theorem A, because in theorem A, we assume the floor homology does not vanish. And this will be, okay, that under some condition, this will be equivalent to saying that the DF is equal to 0. So it is, so when DF is equal to 0, then it's contained in that image for any alpha. So pi check has to be in kernel of alpha for any alpha. Okay, and this will, so, and pi check L in kernel alpha for all alpha is equivalent to saying that pi check L is in the center of GC check. Okay, so that will recover theorem A. Okay, so yeah, so thank you.
Thank you. Are there any questions? What kind of tools do you use to prove theorem A?
Oh, okay. So okay, so for theorem A, so there are two parts. So you need to So if the flow cohomology does not vanish, then you need to show that the moment map is fixed by the while group. Okay, so in fact, it is for this part, it's very easy to prove just few lines. So suppose you have an element such that sigma of you have an element in the while group, so that sigma of mu TL is not equal to mu TL. So it's not fixed by that element in the while group. Yeah, but the left hand side is equal to mu T or sigma L. Yeah. And because the mu sigma L and L, their moment map image are different. So this will imply L intercept sigma L is empty. Yeah. So in particular implies that the flow cohomology L and sigma L is equal to 0. Okay. But sigma L is Hamiltonian isotopic to L because we have a Hamiltonian G action, so sigma L and L are just equivalent. So this gives the HF of L equal to 0. So this is the moment map part. So the similar idea you can show that if the flow cohomology is not equal to 0, then the holonomy is fixed by the while group. It's fixed by the while group. Yeah, but that is still not enough. This because fixing by the while group is not equivalent to saying that it's in the center. So it's up to some finite order thing. So you need to have more analysis for that part.
Okay, thank you. Are there any other questions? Okay, so let's thank Kifung again.
Yeah, thank you.